All right, so dielectrics are sometimes you can put something inside, in between the plates of a parallel capacitor or any capacitor technically. And so what happens, so like normally you have air in here, right? Like, or you have air or nothing in between them, into between these parallel plates, right? And so what you can do is insert another material in there. And what's happening when you insert another material, let's say you put water in there. Well, you shouldn't put water, it's with metal, but let's say you put in some substance in here, right? And it could be another metal, it could be an insulator. It doesn't really matter what it's made up of, but it will effectively increase the capacitance. Okay, and so what it's going to do is, let me kind of explain like how everything's going to be related. Q is equal to CV. Okay, so you're not changing the charge, but let's say like you're not changing the amount of charge, but the increase, the results is going to be that you can have a lower potential difference for the same charge. So you can have a, for the same charge, you can lower the capacitance, and then the potential difference will increase. Oh, sorry, other way around. The capacitance will go up generally when you put something in there, and the potential will go down. Now, why does the capacitance increase for this? This is like an interesting question as to what's happening. What's happening is the dielectric material. Let's say you have positive charges over here, and you have negative charges on the other plate, right? Just like you have for normal capacitor. Now, we can always polarize an insulating material. So polarize, it's going to be made up of tiny positive and negative charges in here. So it's going to be slightly where the negative charges are going to be closer to this side and positive charges are over here. Now, not going to be completely like a conductor. It's a lot easier for that to happen, but it's going to be a slight shift. Okay, and so inside it, because the ions, the molecules will align to where more of the positive charges are on the bottom side towards the negative plate, and more the negative charges are going to be more towards the top. And so what it ends up doing is it creates its own internal electric field within here that will cancel out the electric field. So the electric field ends up going down. So if you look at our voltage, right? So our electric field, which is the negative change in the voltage over the displacement, right? Is to say like, well, because like normally from these charges, the electric field points this way, we're now going to create another electric field inside the dielectric that's going to subtract, it's going to weaken the total electric field in there. So you see the electric field goes down, same distance, so the potential also goes down. So that's another way to think about how the presence of a dielectric is going to cause the potential or the electric field to change. Okay, now the way we model this mathematically is by a dielectric constant kappa. It's purely a property of what the material is. It's how easy it is to polarize it, right? So higher dielectric constants have an easier time polarizing or separating the charges, creating a stronger electric field within the dielectric material. And so the only modification we'll make to the parallel plate capacitors is we'll make this kappa epsilon on A over D. And the smallest value for kappa is 1. Okay, this is kappa. I'm saying the word kappa. It's a Greek letter. It looks like a K. Greek letter kappa is purely property of the dielectric material, and it's generally greater than 1 for anything other than air or vacuum. Air, it's like slightly more than 1. Vacuum is the smallest it's going to be. So when kappa is 1, it goes back to the formula that we've been using for parallel plate capacitors before. So now we're going to use this kappa in there. Okay. So now let's take a look at some examples of here. What's the capacitance with an air-filled capacitor? 2 parallel plates 1 millimeters apart, area of here. So here the kappa is just 1, so it's just epsilon naught A over D. Epsilon naught is 8 point. Let me look up the constant real quick. It's 8.85 times 10 to the negative 12. The area is 8 centimeters, but you got to convert that into this 8 square centimeters. You got to convert that into meters. Right? And so you think of it as like, oh, there's 100 centimeters per meter, right? But you got to square it, right? Let me move that over a little bit so you can see that better. You gotta square it because you gotta convert centimeters squared. So it's over the distance is 1 millimeter, which is 1 times 10 to the negative 3. Okay, and so when you do that, let's do the 8.85 e negative 12 times 8 times 100 squared. Actually, I have it reversed, right? I need centimeter on the denominator. Sorry. I need centimeter on the denominator, cancel that on the numerator. So 1 meter is 100 centimeters. So divide by 100 squared. And then overall divided by 1e negative 3. And I get 7.08 times 10 to the negative 12. 10 to the negative 12 is pico. So this would be farads, or 7.08 picofarads. Okay, the region between the plates is filled with the dielectric, but the material's dielectric constant is 6. What's the new capacitance? Well, the only thing that's going to happen is we're going to multiply by 6 here. So it's going to be 6 times as much. So it's going to be this times 6, which is going to be 42.5 picofarads. It's just going to be times 6. If 10 microcoulombs of charge were on the capacitors, how does the energy compare with and without the dielectric in between? Okay, so here we're going to use U is equal to 1/2 CV, sorry, QV, because we know the charge. So we need to know the potential difference on here, but we know Q is also equal to CV here. Okay, so we can solve for the potential. Now, why do we want to solve for the potentials? Because the potential is not constant. They're giving us a set amount of charge in both cases. And so what we want to do is get rid of the voltage, because we can calculate we know the capacitance and we know the charge. So we want our answer of energy in terms of charge and capacitance. So V is going to be Q over C. This is going to be 1/2 Q squared over C. Okay, so with the no dielectric, the energy is going to be 1/2 10 times micro. This micro is 10 to the negative 6. Right, squared divided by the capacitance, which we've got 7.08 times 10 to the negative 12. Okay, so let's just do that. 0.5 times 10e negative 6 squared divided by this number in our calculator, and I get 7.06 joules. Okay, and then with the dielectric, you can think of it this way. This is going to be 6 times as much. It's going to have less energy, right? So it's going to be 1/2 10 times 10 to the negative 6 squared divided by the 42 times 10 to the negative 12. Or you can think of it as I'm just going to divide this by 6, which is going to be 1.18 joules here. Because the charge is constant, but we're just changing the amount of capacitance, right? And so the energy changes, right? And that's going to happen when we have the dielectric. That's a consequence of some of the math in there. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.